So this is the video for class Monday, February 1st. The plan is to cover the next section of chapter 2, which we've been working in, applications of integration. But before we can do the next application, we need to review something from Calculus 1. In your Calculus 1 book, this theorem would be presented in chapter 4. It's a theorem called the mean value theorem. In my classes last fall, I don't remember that we talked about it. If we did, not very much. The reason is it was only in Calc 1, it's only kind of a theoretical result. We don't use it much, but now here in Calc 2, we need to use it, at least for this application that we're looking at in chapter 2. And so I just want to cover it quickly. I'll probably assign some problems dealing with it just so you can get comfortable with it. It says something that's real sort of common sense. And I've drawn a picture hopefully to illustrate that. It has some conditions to be met. The first one is that we need a function to be continuous on a closed interval. Both of those things are essential for us to be able to guarantee the theorem's result. And the third thing we need is the function needs to be differentiable. Remember, that means the graph has no cusps or vertical tangents, and I'll give you an example of why the theorem might not work if that condition is not met. So we need continuous, we need a closed interval, and we need differentiable. It actually only needs to be differentiable on the open interval. That will be enough to guarantee the theorem. And the theorem says then there is a number. We'll call it C. With this property, it's strictly between A and B. It's on the interior of the interval from A to B. And then it has a slope property. So here's the algebraic equation. We can recognize the right-hand side as being the slope of a line segment. Change in y over change in x. And I've illustrated it over here. It's the slope of the line that connects the point A, f of A, with the point B, f of B, just exactly like this blue line does over here. Okay, so the right-hand side of the equation represents the slope of that blue line. And I can interpret the left-hand side as the slope of the tangent line because it's the derivative. And the theorem says if these conditions are met, continuous, differentiable, then this number has to exist, this number C. And I've illustrated in the picture a number. I found the number in the yellow, you can see, between A and B, where it appears the slope of the tangent line there is the same slope as the blue line. If you look a little further, you may realize there is another value of C we could have used, maybe over here somewhere where the tangent line has the same slope. Now, the theorem doesn't guarantee any particular number except one. There has to be 1 point. Now, if we lose differentiability, the theorem may not be true. And let me just give you a graphical example. If we take a function that does not have a derivative at a point, let me draw that in black. Get rid of that. So here's our x-axis, and then let's draw a function that has a cusp right there on the x-axis. So maybe a function like x to the 2/3, although we don't really need to know the algebraic form, is a function like this. So that cusp right there means the derivative doesn't exist. It exists everywhere else, but not at that particular point. There is no unique tangent line there. And so if I make my interval include that point, so let's go from A over here to B over here, and then I'm wondering if the theorem's true. Here is A, f of A Here is B, f of B. So the line that connects those, it's just slightly positive slope. And you can see between A and B, there is no place where the tangent line has the same slope as that line. Okay, so if we lose differentiability, we may lose the statement of the theorem. I could draw a picture where we still had the statement, but we just can't guarantee it if we don't have both conditions, continuity on the closed interval, differentiable on at least the open interval. And let me just do a little problem here. This should slide up out of the way. There it goes. So, real simple problem. Find C as identified in this theorem for the function f of x equals the square root of 5 minus x plus 4 on the interval -1. Actually, let's do -4 up to 1. Okay, this function, its domain, we need 5 minus x to be non-negative, so it has a square root, which says it's defined everywhere less than or equal to 5. Notice our interval only has values that are less than 5. And according to what we learned in first semester calculus, this is kind of a normal function, and it's going to be continuous everywhere on its domain. So we have continuity satisfied in the interval -4 to 1. And also, I'm not going to calculate the derivative. The derivative would have the same domain as the function, except at the value 5. So the domain of f prime, I'm going to let you work out the details. The problem is you're going to get a square root of 5 minus x in the denominator, so x can't be 5. So the domain is every number strictly less than 5, and every number on our interval is less than 5. So it's continuous and differentiable, so the mean value theorem is satisfied. I guess we're going to need the derivative anyway to find the value of c, so let's calculate it. F prime of x equals, using the chain rule, remember 1 over 2 square roots times the derivative of the inside. The derivative of 4 is 0. So let's write that as -1 over 2 square roots. And now the equation that we need to solve, we need to find the value of c such that when I plug it into the derivative, I get the function evaluated. See if I can get that information down a little bit lower. Come on, slide. Doesn't want to slide down. So here is the function over here. And let's write it down below. Square root 5 minus x plus 4. Square root 5 minus x plus 4. And the interval is -4 to 1. When you plug a 1 in there, you get the square root of 4 plus 4, minus when you plug in a -4, you get the square root of 9 plus 4. And down below we get 1 minus -4. So that's the right-hand side. F of b minus f of a divided by b minus a. And simplify that, I get 6 minus 7. All right, square root 4 is 2, plus 4 is 6. Square root 9 is 3, plus 4 is 7. 6 minus 7 over 5. So the slope of the so-called secant line is negative 1/5. And now we want to solve this equation where this thing is equal to that thing. That's what we need to solve. Let's cross multiply. Notice the minus signs are going to cancel out. So we'll do that. And then I'm going to get 2 square root 5 minus c equals 5. And so the square root of 5 minus c equals 5 halves. Square both sides. 5 minus c equals 25 fourths. And therefore c equals 5 minus 25 fourths. Well, 5 is 20 fourths. So we get negative 5 fourths. And remember, our interval was minus 4 to 1. So this number is very definitely on the interval. Unlike the picture I drew, there's only one number, evidently only one solution to our equation. But we found it. So we showed the mean value theorem was satisfied, and we took it one step further. And for a particular function, we found the value of c that was guaranteed to exist. Now let me pause and set us up for the next thing. All right, so what we really care about is application of the integral, not the mean value theorem, although the mean value theorem is a wonderful theorem. The main advantage the mean value theorem gets us is this algebraic connection between the derivative of a function and the function itself. Okay? Most of the time, we don't really care about the actual number c. I showed you how to calculate one just so we could get a feel for what the mean value theorem says, how it says it. But most of the time, and definitely here in chapter 2, we really don't care about the actual number c. We only really need to know that it exists, and we need to know that it exists inside the interval a to b. Okay, that's what the theorem guarantees us. Now, for integration, if we're going to integrate a function, or a function is involved in an integral, and we're going to assume that the conditions for the mean value theorem are satisfied. In fact, we're going to assume they're satisfied on the whole interval a to b. Again, continuous, differentiable. And if it satisfies those conditions on the whole interval a to b, then it certainly is going to satisfy it on every subinterval inside that interval. So in integration language, the intervals we look at are these little subintervals that we get from a partition, xi minus 1 to xi. And if the function f satisfies the mean value theorem on a to b, then it certainly satisfies it on this subinterval. And therefore, the number c that's guaranteed to exist, it's going to be an interior number here. Okay? So the theorem is going to guarantee that some number exists in here. And, what shall we call it? Well, because I have n of these subintervals, I should index it. So we're going to call it, instead of calling it just a generic c, we're going to call it x sub I. And because it's the very special number that's guaranteed by the mean value theorem, we'll put a little star in the exponent slot. Okay, so we're applying the mean value theorem where a is the left-hand point of the subinterval, b is the right hand, and then xi star is the guaranteed number that exists in the interval. And when we think about the mean value theorem, we're going to think about it in this form right here, change in y. That's what a slope calculation is. Change in y over change in x. All right, I think that's the preliminaries, and now we're ready to apply it in chapter 2. So let me set that thing up. I'll be right back. All right, so the application we want to talk about technically is called arc length. And all that means is the length of a defined curve. Okay, and the way we're going to think about it pretty much always is we have a graph of a function. We're going to start at the point A, actually the point A, f of A. And then we're going to travel along the curve, eventually arriving at the point B, f of B. And we'll ask the question, traveling on that curve, how far have we gone? How long is this curve? Length of the curve, how long is it? From here, well, it's obviously bigger than B minus A. B minus A would be the straight line direction. And because our curve meanders around a little bit, it's a bigger number than that. But how long is it? Well, what can geometry tell us? Well, if the curve was actually a line, we could just use the distance formula, not a calculus problem. If the curve was on the rim of a circle and we knew the angle theta that generated it, so here's my curve. I'll draw it in blue, like just there, and I happen to know this angle in radian measure, then I could get the length of the curve without calculus. S would just be the radius of the circle times the radian measure. Okay, those are pretty much the only two cases that I know of that geometry can solve this problem for us. Every other curve, it's a calculus problem. Okay, so let's dig in and see if we can solve it. As always, we're going to split our interval A to B into n equal parts. We're assuming, because it turns out we're going to need the mean value theorem. So this method only works for functions that are continuous on the closed interval A to B and differentiable on the open interval, just exactly like the graph I drew. If we don't have that condition met, then maybe we'll never run into a problem like that. If we do, there are ways to deal with it, and we'll save it for when it happens. All right, so just like we always do, we take a little subinterval. Let me imagine here is an xi minus 1, and here is an xi. Let me blow that interval up so we can get a little bit better picture. So here's a piece of the x-axis, xi minus 1, xi. Above it, the curve is doing something, maybe like that. And so we're going to apply the mean value theorem to this little interval here. But first, we'll do a few things. Now, I hope it's clear that a really, really good estimate for the curve is the straight line that connects these points. Okay? Especially if you think about we need our estimate to go away as the partition gets finer, and that certainly has that feel to it. Okay? And so we're going to use the length of this line, and let's call it D, as an estimate of the length of the curve. Okay, so that D distance we're using can be thought of as the hypotenuse of a right triangle. And we can label the legs of that triangle. Well, this guy here is none other than delta x, right? He's the width of the subinterval. And then we can just think about this as delta y. It's how much y changes over this little subinterval. And then the distance, we'll call it d sub I because we're on the ith subinterval. We'll put a little sub I. It's just by Pythagorean's theorem. It's the square root of delta x squared plus delta y squared. Okay, pretty straightforward, I think. Just use the hypotenuse to approximate the curve, and you can imagine if we shrink this interval down, that's just going to be a perfect estimate. So here's what my distances look like, and unfortunately, or maybe if we like solving problems fortunately, there's a delta x in there, but it's messed up. It's squared, and then it's added to delta y, and all that's under the square root. So, of course, what we're looking for is, some sort of a function. I'll call it g of xi star times delta x. That's what we're looking for, because then we can turn that into a Riemann sum. And we're a long ways away from that. So let's see what we can do. There's an old trick in mathematics which says, like, if you need something to have a certain form, we need a delta x out here, then you just make it happen. You put it there and say, what sort of price do we have to pay? So I really, really need a delta x right there. Well, if I multiply the top, I still want to talk about the distance. I'm not interested in changing that. So I need to divide by delta x as well. And now I'm multiplying by 1. And while it looks a little bit different, it has the same value. All right, then we're going to take the 1 in the denominator that we don't need, make a big square root here, and push it under the radical sign. We'll do this a slow step at a time. Well, if I push him under a radical sign, I got to square him. Okay? So then I have my delta x at the end just fine, but so far I don't have this, the other part expressed as a value that lies in the subinterval. But we got a ways to go. Let's simplify that radical. I can write it as 2 fractions. Let me do this in yellow. This fraction right here, hopefully you can recognize as 1. Delta x squared over delta x squared. Let's go back to black for the details. And then I have delta y over delta x squared. I can pull the square out of those things and write it like that. Okay? Now, the mean value theorem. We showed that we can write the derivative at let me say it this way, that dy, delta y over delta x, by the mean value theorem, we'll abbreviate MVT, we can write as f primed of some number on the interval. Well, because we're focused on this little subinterval, we'll call that number, instead of c like we showed on the earlier screen, we're going to call it xi star, and I know by the mean value theorem it's somewhere on this subinterval. And so we get this amazing thing. 1 plus, replace delta y, delta x with f primed of xi star squared, and then we have our delta x. And guess what? That looks like the term of a Riemann sum. So then, most of the hard work is done. The distance, the total distance, is going to be approximated by, if I sum those over all subintervals, there are n of them, I get the square root of 1 plus f primed of xi star squared delta x. This is a Riemann sum. And therefore, if we take the limit as n goes to infinity, we get the integral, the distance, and the limit, the error goes away, and the distance is exactly equal to the integral across the interval a to b. Now here's the function. Put it in blue. Whatever shows up between the sigma and the delta x, that's what we integrate. So 1 plus square root 1 plus f primed of x. X star becomes x in the integral dx. And there is our formula. Now, like all the other formulas we derived, maybe some of the steps we took to get here are still a little fuzzy in your mind. That's okay. Can you read this formula? Can you use it? I think so, and that's what we need to do from now on. All right, let's try a problem. Oh, first let me say this. Let me pause and set this. All right, here is the formula we derived earlier. And there's sort of good news, bad news about this integral. I'll tell you the bad news first. So if you look at the function that we have to integrate, that is, we need an antiderivative for. So that's a weird combination. We take the function f, and it turns out the functional values don't even matter. The arc length, the only ones that matter are its derivatives. And that makes sense. The slope of the line would convey some kind of information about the distance, how long the curve is, not the functional values themselves. Certainly, if we took a function like this and then we subtracted a constant from it, so those have the same length. So the actual functional values aren't important, rather the slopes. That's one thing we learned. But just the things we have to do for a given function, take the derivative and then square it and then add 1 to it and then take the square root and then look at that whole thing and say, can we find an antiderivative? The bad news is we will almost never be able to find an antiderivative. Okay, there are some carefully chosen functions, and I'll do at least one example, where we can find an antiderivative, and therefore we can use the fundamental theorem to find the value. Okay, that's the bad news. It's hard for almost all functions. We cannot use the fundamental theorem. So what's our alternative to the fundamental theorem? Well, it's our calculators. And our calculators, even if there is no antiderivative, they can tell us in almost all cases what number this is, at least within super accuracy, if not exactly. So that's what we're looking for, a number represented by this integral. And even if we can't find an antiderivative, our calculators can tell us within a great deal of accuracy what the number is. And so for almost all functions, to actually find the value of the integral, this is a calculator problem. And we'll talk about what that means on the exam. And I wouldn't worry about it if you feel inclined to worry about it. So for example, let's go to black. Let's just take a really simple function, y equals x squared. And we'll go on the interval 1 to 5. It's hard to imagine a simpler function than y equals x squared. So we've got a parabola, and now let's pick blue. We're going to go from 1 out here to 5. And I want to know, how long is this curve? So now we have a way to figure it out. We need the derivative. I'll call it f, I guess. Derivative is 2x. 1 plus f primed of x squared is 1 plus, getting ahead of myself, 1 plus 4x squared. And so we need to integrate from 1 to 5 the square root of 1 plus 4x squared. And right now, where we are, chapter 2, calculus 2, we know no antiderivative. We will learn one later on. We don't know it yet. I put a frowny face, although maybe that's really good news. I have a calculator sitting right over there. Let me pause this while I punch it in, and we'll look at the answer. All right, my trusty calculator says that this guy is 24.3953. So on the homework, be sure and read how XYZ expects you to put your answer in. It could save you some grief at getting green instead of red results. I think I shared in class I have a TI-89, and it actually gave me the exact value. Remember, I said we don't know an antiderivative of this function yet, but we'll learn one. Well, my calculator knows what it is. And it's complicated. You would never guess it in a million years. And the first answer I got showed me that long, complicated, which I have to scroll way off my screen to see it all. But then I just asked for a decimal approximation and it gets it to me. All right, in the next chapter, we'll talk about how to find antiderivatives. Maybe not this function, but functions like it. Now, there's a quick way we can think about a rough check if our answer is right, and that is if I just draw a straight line from the point 1, to the point 5, whatever, 26, whatever it is, 25, and find the length of that line, it ought to be just a little bit less than 24.3953 because the curve meanders around a little bit. So we draw this triangle using the distance formula. So the straight line distance is the square root, we'll call it little d. The length of this leg is 4, so we'll square it. And the length of the other leg, the long leg, so this is the point y coordinate 1 here, and this is y coordinate 25. So the length of that leg is 24. So we'll plug it in and square it. And then I asked my calculator that thing. I'll just do it while you're watching here. Square, oops, let's go home. Up, let me pause it while I set it. All right, got it worked out here. Remember, we're trying to find the length of the straight line to compare to the length of the curve. They ought to be pretty close. The line ought to be a little bit smaller. And while I was paused, I found a mistake I occasionally make. That is, the length of the short leg of the triangle is 4. And if you back up the video just a little bit, or maybe you remember, I squared the 4 in my head and plugged in a 16 here. And then I squared it, and so I got a totally ridiculous number, which I knew was wrong, and so I went back and found my mistake. And notice how close it is. That is, if the following the parabola is the scenic route, then there's hardly any cost at traveling it because the lengths are very similar, 24.395 versus 24.3311. But it's in the right order. Of course, when I made the mistake and squared the 4 twice, this number was bigger than that one. And that told me I was making a mistake because the straight line distance is the shortest possible. So found the mistake, everything's good. All right, I want to do another one where we can actually use the fundamental theorem, and this will be sort of a convoluted example. Because here, like this is about as simple as one as you can imagine, x squared. And yet it ran into antiderivative issues. All right, so at least one more example, I'll be back.